Thanks very much, Ryan. Over lunch, it was pointed out by one of the ultrasound people here. How is it that MRI people spend the entire morning talking about acceleration, and the only thing at the end is we get compressed lunching? So I'm not going to talk about acceleration. I'm going to talk about very simple things in terms of low field MR. But this less is more seems to fit very naturally with low field. But I do want to also, as a sort of bridge to the session before lunch, say that I do have a sort of conflict of extra interest of being slightly schizophrenic. In addition to 50 millitesla, I end up trying to do all the hardware for the 14 Tesla whole body magnet, which was just funded by the Dutch Science Foundation, which Camille referred to. But it's also interesting that one of the things we are trying to do there is actually also to simplify that system. And so for 14 Tesla whole body MR will be about the same size as a 3 Tesla. It will be helium, relatively helium free. It's going to be type 2 high temperature superconductor. So we hope that, in fact, rather than things getting more and more and more complicated, we can also add some simplification even to high field MR. But why low field? I mean, we heard from Camille, we heard from Susie about the fantastic advantages of high field and high gradient strength. So why would we think about low field? And I want to then talk about some of the physics and engineering challenges in designing a low field system. And then just to give you an idea about what's the sort of current state of the art. So what can we do in terms of image acquisition and image processing? And that's relatively conventional. And then it's sort of in the spirit, I hope, of this conference. I want to say, let's just take a sledgehammer to the way that we acquire MR data and we interpret MR data. And think about, if we've got a tremendous degree of freedom, what could we actually do, let's say, over the next 5 to 10 years? So there's many, one of the things I really like about this conference is all the different kinds of imaging modalities and all the kind of different mentalities that the people bring. And I think there's a lot of themes which are linked to this talk. And so I want to look at different ways of thinking about rapid and continuous imaging. And then also to borrow, beg, borrow, and steal, but mainly steal from the ultrasound world, which Elisa will talk about, and also a little bit about, indeed, imaging without images, which Sumit will talk about later in the session. And I'm going to talk about low field and just define low field as below 0.1 Tesla. So we're essentially going to be looking at mobile point-of-care MRI systems. And why would we do it? There's 3 reasons. So the first reason is societal. And this is really why we got into this area about 6 years ago. And so if you look at the world's population, 70% has zero and absolutely zero access to MRI. And we've concentrated in sub-Saharan Africa due to some personal connections there. And there, if you go to some of the countries, if you go to Mali, there are 10 million inhabitants and there is 1 radiologist there. So the numbers are quite astounding. So there's simply no MRI, and the conventional MRIs are never going to be a long-term solution. So we want to look and see, can we have accessible, relatively cheap, sustainable MRI where currently there is simply no healthcare? And the other reason is scientific. Let's just think about, we've got a system now that we can completely design from scratch. And we see this in the hackathon that's going on at the moment. Previously, we have to deal with what GE or Siemens or Philips gives us in terms of the magnet. It's always one shape, it's a field strength. We play with it at our peril. Now we can build the magnets which we want. We can look at different geometries. We can look at different ways of encoding. And so I think it opens up an entirely new field. So if we go full scale sort of mad scientist mode, we can think about putting holes in our magnets so we can have people looking at each other as we're doing different experiments. We can have magnets that come open and close. We can have ones where the people are standing up. We can even start to think about scanning magnets where we might have, let's say, an optical tracker over here, and we have a surface magnet that is going over the sort of Star Trek type of thing. We can also think about exercise. If you've got a surface magnet that is on the leg muscle over here, put somebody on the treadmill and see what happens, let's say, to relaxation times. So we can get away from K-space. We can think about continuous sampling and all different kinds of things. So to me, scientifically, this is also a really, really strong driver for going to low field. And also, even in the, let's say, the Western world, high income countries, what we know is that MRI is always at the center here, right? It's at a big medical center like New York or like Leiden in the Netherlands. And it's always the last part of the image. It's the most expensive part. And so if we think about going out in terms of screening or in terms of looking at things at a much earlier stage, out to diagnostic imaging centers or tertiary healthcare, this is also a role that low field MR may play. So what we want to do is essentially copy the concept that other medical imaging modalities have and make portable analogs. And so we know about portable ultrasound. This is a portable OCT, optical coherence tomography, and of course, portable X-rays are very, very common. But you need a clinical reason, right? So I work in a radiology department, but I'm an engineer. So I very much depend upon people saying, this is what something could be useful for. Now, our reason for getting into this, again, with sub-Saharan Africa, was hydrocephalus. It's a disease that doesn't really exist so much in high-income countries. It tends to be adult hydrocephalus. But if you look in sub-Saharan Africa, there's 400,000 pediatric cases every single year. And if you look at, we're not trying to detect it. Everybody can detect it, right? So if you look at a child that has hydrocephalus, you see the swollen ventricles here. The medical intervention then is to put in a shunt and to try and drain that fluid away. And the question is, are you successful or not? Or have you introduced blood into the brain? But there's significant mortality that comes in, and unnecessary mortality, because those measures are not available. Now, if we think about low field MR is going to give us relatively low resolution images at relatively low signal to noise. So we have to choose an application that makes sense from a clinical point of view. And if we're just trying to look at CSF, which is obviously the bright thing here, we don't need great image contrast. We don't need great spatial resolution. So initially, when we talked to our colleagues, we were looking at something like 3 by 3 by 10 cubic millimeters, and that would be sufficient. And I'll show you results that actually we've done a lot better than that, and other groups equally well. So this was really the driving force to start off with. So what are the physics challenges, and how do we try and engineer these to overcome them? So there are 3 big enemies, right? The first one is, depending on the day, signal to noise, or sometimes noise to signal, depending on how much interference there is and how well your hardware is working. And that's the primary one. The second one is the inhomogeneity of the main magnetic field. Because we're going to be building a system which is very, very small, which is portable, the head is very close to the actual magnet itself. And that means that the inhomogeneity is going to be far, far greater, orders of magnitude greater, than if you can have a very large superconducting magnet, which is well away from the head that you're studying. And the third thing is actually diffusion. And diffusion, I'll come back to this because I want to talk about surface magnets at the end of the talk. And then diffusion is a big problem because you may have gradients here even higher than the ones that Susie were talking about in terms of Teslas per meter. And that's when we start talking about surface magnets is the big enemy. So what are the challenges? Signal to noise. Camille looked at the signal to noise, gave us the equations for this. And then 3 Tesla to 50 millitesla, which is where we're operating, factor of over 1,000. So if you take for an equal signal to noise image at 3T, then your 1-minute scan becomes 3 years, which is slightly intimidating. Or you say, okay, we have to go to lower spatial resolution, and then our standard 1 by 1 by 3, let's say, becomes order of magnitude 10 by 10 by 30, and you end up with something that looks like a potassium image, and it's utterly useless from a clinical point of view. So we're going to have to do something, both from the MR physics point of view and also the engineering point of view, to improve this. And since we've had a great talks on astronomy, I quickly came up with what I hope is a good analogy. You will hear, unfortunately, at various conferences that people will say, using various imaging processing techniques, you can turn a 50 millitesla image into a 3 Tesla image. And it will look the same, it'll have the same signal to noise. If we look from an astronomy point of view, just running the numbers, I think this is a true thing. This is equivalent to saying a 200-inch reflector on Mount Palomar, which when I was growing up was the largest optical mirror, will give you the same signal to noise as this Skywatcher telescope for 715 euros, which is basically a 2-inch reflector. If you've got that, then I would argue that you've got a problem with your 200-inch reflector as opposed to the other way around. And it's the same way here, right? Whatever we do, whatever we're going to talk about, our 50 millitesla magnet is not going to get you an image that looks like a 3 Tesla. But if you think about actually what you can see with that 2-inch reflector, you can see the moons of Jupiter and you can see the rings of Saturn. So this is not the James Webb telescope, but you can still get, you know, relatively interesting astronomical information. And let's look at the advantages of low field. So if we can overcome some of these issues, then we have no sighting costs, right? No power, no cooling, no taking Charleston down for 20 seconds. The medical implants give us 0 susceptibility artifacts. If we take a screw, a spinal screw, we can see the pitch on that screw. If we take a cardiac stent, you can see the flow inside that cardiac stent. SAR, we can't heat somebody up if we tried. And we did try and get a publication. We still couldn't heat anything up with that. Contraindications, you know, you worry about something being half a wavelength long, that's 75 meters. If you have something that's inside you 75 meters, you have bigger problems than going into a low field MRI. Essentially, it's great. It's silent because of Lorentz forces. And where we start to get back is we've got short T1 relaxation times. We can pulse much faster. We can pulse with full 180-degree pulses. And so we can run very, very efficient sequences. So we can start to get back some of that SNR by using, you know, the MR physics. And really, I think the paper that showed us this is feasible is if you go back, and we're going to have a talk about a totally different topic by the last author, Ron Walsworth here, who had this very low 6.5 millitesla scanner, and he used it initially for helium. And then about a decade later, Mathieu Saracani showed these images where using balanced SSFP, you know, this is 6.5 millitesla. This was wow. If you can get those kind of images, then we should be able to build something at 50 millitesla, which is actually going to be useful. This really was sort of the eye opener, I think, for a lot of people. So what are we going to do? We have to design this system. We're going to image pediatric brains, and this system has to cost 2% of the cost. If this costs 50% of a 1.5 Tesla scanner, go and buy a 1.5 Tesla scanner, right? So it's got to be of the order of 10, 20,000 euros. No shielded room, no cooling. It's got to plug into the wall. We can't have radiologists or radiographers looking at this and running it. So it has to be run by somebody who can literally press the on button, and it's got to be portable. So what do we have to do then? That means it's got to be made of permanent magnets. We can't be using electromagnets or superconducting magnets. We've got to be able to reject outside noise. Ideally, because we want this to be something where all the plans are available for fixing. We don't want maintenance contracts and things like that. We want to go open source, the same way that Lior and his team is doing for the hackathon. So we need to be able to 3D print stuff. We need to be able to repair stuff. As you said, it's got to go run off mains. We can also actually run our things off batteries. And so how do we design this? I don't want to go into this in great detail, but there is an assumption that low field is easy. And low field isn't easy. It's no easier than high field. Because of this, the signal to noise, if we lose a factor of 2, we're done, right? If you lose a factor of 2 on your 3T, who cares, really? So the way we design this is in an iterative loop. So this is the only time I'm going to use iterative in this talk, because every single component has an effect on every other component. So if you make a magnet slightly bigger, it will have an effect on weight. It will have an effect on B0 homogeneity and B0 strength. That will affect your signal to noise, but it means your RF shield can get slightly further away from your transmit coil, which means that it'll be more efficient, which means your amplifier doesn't need much power, which means you can get higher signal to noise, which may or may not balance out the fact that you made the magnet bigger. So your B0, your gradients, your RF, everything has an effect. So basically you have to say, I want a system that weighs this amount, that gives me signal to noise with this amount with the resolution of this. And then if you have those sort of inputs over here, we've designed something that will come up with the magnet design. And interestingly, so you'll end up then with a magnet here with different dimensions. So you see those, the radius of the rings here changes. you'll end up with 3 gradient coils and you'll end up with an RF coil. And notice that actually one of your gradients may actually be outside your magnet. And that again is to do with the whole sensitivity and how much gradient strength you need for certain resolution. So you can end up with some different kinds of geometry. I know the MGH group also has looked at this and also come up with designs where you do indeed put the gradient outside. So what do we end up with? Well, we end up with a system that looks like this after a lot of work. So this is a system which, depending on where you are, weighs about 100 kilograms or 220 pounds if you're over here, if you're in the UK, 16 stone. I haven't mentioned AI. I've got up to slide 21 without mentioning AI. It's said that the EMI reduction, electromagnetic interference reduction, is a big thing. There's been many techniques that have come up with this. So Will Grissom's group has been looking at the editor technique. Ed Wu's group has been looking at software-based AI. I'm the kind of person who honestly can't really work out my phone in terms of technology. And so our AI comes up with this. So this is using a shield which is made of aluminum. And so this is our AI shielding. Now, as some of you can tell from my accent, in fact, working in the UK, I have a much bigger advantage because I can use aluminium. And aluminium then is an AI squared, which sort of gives us a factor of intelligence improvement, right, in terms of EMI reduction. What you know now is that every single talk here has one slide that is going on to Twitter or X, and that is going to be the one that is going to go on from this talk, and I'm going to be in a lot of trouble afterwards. We open source everything, and so if you look at the magnet design here, there's some tools here, which I think actually probably going to be updated by Lior and his team at the hackathon. The gradient coils, the RF coils are 3D printed. Again, you can do a gradient design tool over here. All the electronics then is online, again, for easy repair. And here's the gradient amplifier and the RF amplifier. And again, those are relatively low power, so those can be run off batteries. We put this entire system sort of similar to the hackathon. As I said, we work with Uganda, and we really wanted to be in a situation where we weren't just saying, okay, here's a magnet. Good luck. So we went on site, we shipped the components over there. We had a workshop where we taught some MRI, but we also had 6 students from all of biomedical engineering all over Africa who came in, and they built this MRI system. And I think it took about 11 days for them to build this from scratch. And it's a system that has broken twice and has been fixed twice on site. And again, this idea of sort of sustainability and accessibility and on-site, I think, is incredibly important if we look on this type of project. It's also interesting, there's a lot of urban myths. You know, many people said, yeah, but low field was in the 80s and 90s. It's absolutely true. And if you look at some of those papers, you know, you'll read the coil losses dominated low field, and they don't. And capacitive segmentation isn't necessary, and it is. And Litz wire, you can only use to certain frequencies. Well, that's not actually true. And pin diodes don't work. Well, they do. So you get the idea here. And parallel imaging isn't effective, and actually it is. So, you know, there's been some interesting sort of learning lessons as we go along. So does it work? Let me just show you current state of the art of what we have. So this is just our particular system. So this is my brain. And again, this is running at a resolution which is not a 3T resolution. So this is, you know, 2 by 2 by 3 millimeters. This is a sort of proton density stroke T1 weighted image over here. And this is a sequence where we just try and do the CSF, right? So we just want to go as fast as possible. So it's a slightly modified T2 sequence. So does it look like a 3 Tesla image? No, certainly doesn't. But does it look like an image that came out of 2000 fridge magnets? No, also no, right? So it's for us, it's still kind of a little bit of magic in terms of the image quality that comes out. And of course, other groups, like I said, Clarissa Cooley at MGH, who's here, has a system with slightly higher magnetic field and has this very nice feature where she has an inbuilt gradient. And then Ed Wu's group at Hong Kong has really been doing a lot of work the past year with a slightly different magnet design, but again, the same field strength. And I think Ed's group really shows that there are certain clinical cases where, you know, if you look at this subacute ischemic stroke, this is not a subtle thing, right? This is something you and I can pick out. But the information you get diagnostically from a 55 millitesla system is identical to what you get at a 3 Tesla system in that case. If it was 0.5 millimeter in size, we'd miss it and the 3 Tesla would get it. So again, it's a question of marrying the technology to the particular clinical application. And of course, Hyperfine then has commercialized this kind of double pole piece C-shaped magnet. And here's some work we're doing with them in Mbale. And this is a kid with hydrocephalus, right? It's kind of a shocking image. So why do you need a 3T scanner there? You don't need a 3T scanner. You can get absolutely all the information you need from a 64 millitesla scanner. So sometimes, one asks the question, why not just use a 3T? I think this gives the answer in this particular application. So open questions I have are sort of, how close are we to the ultimate intrinsic SNR? And not the ultimate intrinsic SNR from a high field point of view, because the way we want to look at this is totally different. We don't need an electrodynamics approach. We'd need more a kind of system approach there. So I'm kind of interested to see what people's point of view. And then, okay, let's be provocative. Is AI useful or necessary or utterly useless for low field MR? So I won't say totally useless, so John doesn't kill me, but I think we have to be very careful about where we use it. So where most people use it is image denoising, right? So here's an unprocessed image, and we worked with, again, training data sets acquired from 3T. This was provided by Philips. And here's our AI denoised, and here's our AI denoised plus single image super resolution. It looks pretty nice, right? So AI is doing a pretty good job. So why would I say, is it useless? Well, if we look at lots and lots of different flavors of AI on a relatively low contrast image, relatively low resolution, I can just put on a BM4D filter and I can get essentially the same results. So not to say that you don't need AI or AI is doing anything bad, but this may be a situation where the type of data we're getting out is simply going to be well addressed by a well-designed filter. And then we don't need to worry about training data sets. And if we're talking about low middle income countries, we're not going to be able to get large amounts of training data sets. So open question, very willing to be attacked and to my mind to be changed on that. So new ways of not imaging, let me finish. Then we always think about case space, right? That whatever we talk about continuous imaging, we talk about how we acquire data, we talk about spokes, we talk about everything. It's always about case space. And we're always limited by MR relaxation times. We cannot acquire. So even when we talk about continuous, and that great talk yesterday, we're not acquiring all the time. We acquire continuously in one sense, but there are still big gaps where we're putting in pulses and we're waiting for T1 and all those irritating things. So can we get beyond that? And again, let's just steal somebody else's idea rather than reinvent the wheel. And let's go back to this EEG. So here's an EEG, and if you know anything about EEGs, which none of us do, you will be able to pick out that there's a focal cortical dysplasia in a certain part of the brain. Now, to us, it looks like noise, right? Or structured noise. Are you going to form an image from that? You can't form an image from that, right? It would be totally useless to try and take that data and form an image. The data and the information is there in those traces, in whatever a fingerprint of those signals are. You can think about ultrasound as another example, where if you look at, you have a kid who has fluid in the lungs or a kid who doesn't. You take an ultrasound, you do an A mode scan, just one shot out and back, takes 10 milliseconds. How do you tell if the liquid is there? You're going to see that if it isn't there, the ultrasound is going to bounce backwards and forwards and you're going to see reverberation. And if the fluid is there, it's not going to do that. It's going to go through. So again, if you know about ultrasound, you know about this. So there's just patterns. Take an example here. We've got two possibilities. We've got a brain that has, let's say, a hematoma over here, or has something that is with iron, let's say, or blood over here. Is it on the left side or the right side? There's been a traffic accident, very, very common in low middle income countries, and one of the reasons they're interested. So what do? We might take a surface magnet and just put it on the left side or the right side. Now, let's suppose we get two signals out, and those two signals look like this. Every person who knows about MR will be able to tell you which side that is if you're left or right. Right? Because of the T2, because of the reduced T2, because of the blood. If you're from astronomy, you probably can't tell that, but it's something about, that there is information in there if we want to pull it out. And that, I think, is where AI could be extremely useful, because we're going to end up with noisy signals, we're going to end up with lots of different variants and things like that. And this idea sounds kind of crazy. There is an FDA-approved infrascanner, and that infrascanner is an infrared scanner that is used in about 6 different positions. So you see it either goes green or it goes red over here And the same idea is to try and pick up something over here. And again, it's not forming an image. It's giving you, 5 or 6 green or maybe 1 red over here. So it's not such a crazy idea. It's not what we think about in terms of MR, but the concept here might be useful. And how would we do that in practice? Well, we would look at a surface magnet, and these are starting to be used. Many papers now coming from the MGH group and others. And we basically use a surface magnet. The surface magnet can be constructed so that we either get sort of a saddle point here, where the field is relatively homogeneous, or we deliberately have, again, a gradient over here. So with that gradient, of course, we can look at the resonant frequency being very, very different as a function of depth. And how do we cover that? Well, we might look at solving the spatial encoding and the relaxation time at once by, again, borrowing and stealing from optical coherence tomography, which is a system where the source and the receiver are swept very rapidly through different frequencies. And so since we're interrogating very, very small areas, as a function of time, we don't need to worry about relaxation, and we're also getting spatial information because of that linear gradient in the magnetic field. So some ideas just on how we might be looking at non-image-based MRI. And again, this kind of thing comes into ultrasound. So some things I think that Elisa may talk about have these very, very high temporal rates of ultrasound. I want to end off with one of the things, if I go to this summary here, is I think low field has a role in healthcare, particularly in low middle income countries. It additionally, and I'll come back to the slide previously of this, gives us a chance to, in these countries, retain young researchers who don't have any facilities locally. And the reason I say that is this is the ISMRM African chapter was formed. It had its first meeting 2 weeks ago in Ghana, in Accra. The number of countries in ISMRM, which has been around for 40 years, went instantaneously from 58 to 112. Every single student there was incredibly enthusiastic, and every single person wanted to leave. Why? Because they want to do research and they don't have local facilities, because to get onto a 1.5 Tesla scanner is not possible because it's used for clinical use and it's incredibly expensive. So I hope that things like the systems being built by Lior and that I've shown might also play a role. And let's be honest, it's just fun to think what you can do with low field. Thanks very much.
Thank you very much, Andrew. We are a little bit over time, but I'd like to open up the floor for just a quick question. If anyone has any, Andrew opened himself up there. I'm just kind of curious about dissemination. I guess that's maybe will take care of itself based on what you've seen already from the workshop here.
I think dissemination will take care. I think we have one thing I don't want to end on a negative note. You know, this is not going to change in 5 years or 10 years. This is a 50-year project, right? In terms of there's going to be ups and downs. We have to deal with lots of different issues. But I think if there's a constant push and a constant force, and a lot of people get involved in this, I think the dissemination can continue. But there's lots of barriers, so we just have to be aware of that.
Just one quick one, Andrew. Tour de force as always. Thank you. You talked about imaging or generating signatures rather than images. One of the interesting things that happens then, though, as you kind of showed, is your equipment changes depending upon what signature you're looking for, right? And we're used to an MR machine as sort of a one-size-fits-all, we can see anything type of machine. So can you talk a little bit about the diversity of scanners or sensors you might be generating, and is there any way to hold that in control, or do we just back off and embrace the diversity?
Oh, back off and embrace diversity always. But I mean, how many ultrasound scanners are there in NYU? In radiology, in all the different ologies around, there's probably 100. And I would guess they're all working at slightly different frequencies. You're going to have the high frequency ones for low penetration. You're going to have, I think that's the analogy to look at. We're not going to be quite as widespread as that, but there is no problem that you've got 10 different ultrasound systems, each of which has 3 different transducers. So I like I said, embrace diversity.